In this video, we'll introduce you the principle of visual displacement, and hopefully we can see something that is fairly useful for us to use. This is your stress strain curve. As you can see, this is a stress, there's a strain over here. Alright, this is the elastic region. This is the non-elastic, non-linear system, okay, or where you start to deform your stuff, etc. Okay, and therefore we are looking only at this portion over here, elastic region, for the principal visual displacement. And therefore what we're still dealing with are just the stress is equals to E epsilon, just for you to note. Okay, and we know that the force is proportional to the stresses, right? Because force is equals to stress times area, so it's somewhat proportional. And we also know that the strain is also proportional to the U, the X, meaning your displacement of your bar. If you remember just now, there'll be some displacement du. Alright, so in our case, we are just simply talking about certain displacement, that's all. So certain displacement is just simply some u, not a small displacement du. But anyway, you get what I mean, right? So therefore, it's that meaning. So they are somewhat proportional to each other. Okay, with this proportionality, whatever, we want to actually look into this area under this curve, this elastic region over here. What is the area under this region? Alright, and this region, what we call is, it's your strain energy. Right, area under a curve is strain energy. So the area under a curve is somewhat talking about some forces. Alright, multiply by certain, you can say strain, or you can multiply by u. In our case, I just multiply by u, so I'll have F multiplied by u. Alright, and then because it's a triangular, alright, so F times u divided by 2. Right, so you have half Fu, okay? Because you can see the stress, right, is in terms of the strain, so the forces will be in terms of the displacement, okay? So you just need to take note of this. Alright, as you can see, the stress is in terms of the strain, and for our forces, we will be in terms of our displacement. Alright, so half Fu is equals to, if you know that the force is equals to stress times your area, so therefore I'll just simply sub in as this. So half, alright, F is equals to stress times the area, alright, multiplied by your U. Okay, ta-da! And next what we're gonna do is to rearrange the U. Since you know that the strain is equals to your displacement divided by your original length. Previously was the U over your original length, right? But this write as U over your original length. So I just want to return U, alright, so therefore I'll just simply write as the epsilon, the strain times the length is equals to your displacement. Okay, so what I'm gonna left with is multiply by your length times your strain, alright, because your U is simply your L length times your epsilon, same thing over here. So I'm just simply subbing in your stuff, okay? As you can see, A and L are simply, if you multiply all of them together, what you have is half. Alright, just bring this epsilon to the other side. So you have half strain. Instead of AL, I'll just write as dV. Okay. So up till now, just to update with you, what we have done is just simply taking the area under this curve, this elastic curve. We do some subbings and things like that only. Alright, I didn't cheat your feeling of doing any other stuff. Okay, just area under the curve, that's all. Okay, so in our case right now, you will see that your half Fu is equals to your half this dude over there. And simply take this, just bring it all over to this side. Okay. Next, I'm gonna cancel away the half, because if I were to bring this 2 upwards over here, you have like 2 divided by 2, 1. So in other words, I'll cancel them off. Okay, so if I were to cancel them off, I have this thing over here. Okay, so since I see that there is a dV over here, alright, I'll just simply integrate them since I know that there's some small changes. Okay, and then I want to set it as an equilibrium equation. So I have Fu minus your stress strain dV is equals to 0. Okay, So what is FU and what is this thing over here? Okay, FU, which we have started off with just now, which what we have talked about is this thing over here, right? But I actually didn't define to you what is the actual meaning, right? Because I want to leave it to here to together explain to you what it's all about. Right, the FU itself is the work done. Because if you remember, work done is force times distance. Your force times your displacement. It's the same thing with your work done. Minus away your stress strain. Why is your stress strain talking about? Your stress and strain all together on a certain volume, we call this the strain energy. Okay, is equals to 0. So your work done must be equals to your strain energy. Okay? We're just simply stating all the equation based on what is area under this curve only. And this area under this curve is the strain energy. Alright? Whilst the strain energy is in terms of the work done you have done to the system. That's why we have force proportional to your stress and your strain proportional to your displacement. Alright, and then things like that, and then simply shown over here already. Okay, I hope that this is pretty clear. And therefore, what is principle of the virtual displacement? The principle of the virtual displacement is just simply a certain virtual displacement. You somewhat simulate to tell us that you may have a certain small little changes of u. Alright, it's a virtual displacement, as if you didn't exist at all. But just to illustrate explicitly to you that there is a certain small little displacement for calculation purposes or for computational purposes. Alright, so you have a certain u, v indicates that it's a virtual displacement. Alright, so based on these things, alright, instead of just our displacement itself all over here, I'll just simply write them as a virtual. This is why I didn't actually define them at first, because I don't want to confuse you. So all this stuff I'll just simply write them over here. So the u I'll just simply write as a virtual. Your strain I'll write as a virtual because the strain is proportional to your u and your over L. Okay, so therefore I just hope that this is pretty clear. This at first is work done minus strain energy. In terms of a virtual, is just simply a virtual work done minus virtual strain energy. Just the meaning of that. Alright. Now the next question that raises to us is that what if we are talking about instead of 1D, as you can see this equation is of 1D. 1 force, 1 displacement, 1 stress, 1 epsilon, right? Actually the stress is always the same for all. And then never mind. Let's just keep it to this way first. This is all 1D. But what if this is 2D, this is 3D? Alright, your forces may be in 3 directions now. Right, you may have F1, F2, F3. Okay? But take note of this basic concept is that FU, alright, or FU virtual, alright, is a value, right? It's some 3 or 4, whatever. It's in terms of the work done. It must be a scalar value. So if it must be a scalar value, we are talking about force transpose U. Okay, maybe I should write it in terms of a matrix U, because we're talking about inner product. Inner product is a dot product. Dot product gives you a scalar, right? So therefore you need to know this. Alright, so I'll just simply rewrite your FU as a FU this thing, I mean with a virtual. Alright, so this thing over here is simply a scalar still. Alright, but in terms of a 3D or 4D, whatever it is, it's some vectors only. Alright, for your stress strain, I'll just simply leave them as this one first. Okay, you may tell me that there is a lot of stresses in different directions, but in our case, in a bar system, alright, I don't know how. If you still remember, your stresses is in terms of stress 1, 1, stress 1, 2, stress 1, 2, and stress 2, 2. Something of that form. But we just keep it as a simple some stress, and that's all, with a certain virtual displacement or certain strain, virtual strain. Alright, so we just leave this as a general equation, telling people that this whole thing over here is your work done. This whole thing over here is just simply your strain energy, alright, taken all across your whole volume of your cube or whatever things. So from here we can somewhat see that your stresses are in terms of just one stress only. Later on, if I see that there is more stresses, then I'll just update over here. but so far you just leave it as this form, okay? But nonetheless, this whole equation, although it's very complex now in terms of matrix or whatsoever, it's just the area under this curve. Macam only, but anyway, yeah, it's area under this curve. Yeah, okay, so that's all, and I shall see you soon. This is just a virtual displacement, and I shall see you soon to how do we derive other stuff using this. See you there.